shit.
That's what I'm talking about.
Wait.
Okay, now, from the beginning.
Let's get started. My name's Eric Mauskopf. I'm a product manager at Google. I work on our spatial audio product. And today we're going to be talking about resonance audio, spatial audio, quality, and speed. So there are three topics we're going to cover today. We're going to start off with a high-level overview and show off a few of the most recent features that we launched. Then we're going to go into a deep dive into Ambisonics, and we'll wrap up with a fast-paced tour of our DSP library. So Resonance Audio is a spatial audio SDK that's cross-platform and highly optimized for both mobile and desktop computing. And it comes with game engine plugins for the top. It comes with plugins for the top game engines, audio engines, digital audio workstations, as well as native SDKs for Android, iOS, the web, and most recently we released a C++ interface directly to our DSP library. And we're very excited to announce that just last week we open sourced the Resonance Audio project. So not only do you have access to all of these plugins and SDKs, but you can adapt them to any platform you're working on, no matter where you work. You just need to head over to our GitHub and download it, and you can get started. So the Resonance Audio SDK plugin for Unity has a comprehensive set of features that span direct sound as well as reflections and reverb. I've highlighted a few of the most recent features that we launched here, and we'll cover a couple of them in the talk today. Geometry-based reverb as well as ambisonic recording are two of those features that we'll dive into a little bit. Before we do that, let's take a look at a basic Unity scene. Let's say you have an object like this guitar, and you want to spatialize the sound that the guitar is producing. All you need to do is import our plugin into your Unity project, set it as the default spatializer, and you can use the standard Unity audio source and attach it to that game object. And our plugin will automatically spatialize the sound that's coming from that object based on where it is and where your listener is in the scene. But more interestingly, we have two additional properties that are exposed through a Resonance Audio plugin that goes on top of the basic Unity audio source. And that's directivity as well as occlusion. So let's start with directivity. Let's say you're walking around this guitar in the real world. And you would imagine that it would sound differently depending on what side of the guitar you're standing on. So for instance, if you're standing in front of the guitar, then you would imagine it's going to sound louder than if you're standing behind it. Our directivity plugin gives you precise control on how this works in your environment. And as seen here, you can control the shape of the directivity pattern to control how it should sound when approached from different angles all around the object. This is our alpha parameter adjustment. But furthermore, we have a sharpness parameter that you can smoothly adjust the width of the directivity beam accordingly. So by choosing the right alpha and sharpness values, you can closely match the directivity of real-world sources in your virtual environment. Now, the sound of the guitar in this example should be blocked by the wall when you're out of view. And with the occlusion plugin enabled in Unity, we automatically detect all the physical colliders in the scene, which occlude the source path to the listener, and apply this effect accordingly in real time. Then, to simulate the effects of the acoustic environment itself and generate some reverb, we have what we call Resonance Audio Rooms. And with this component, we offer a wide range of parameters for you to adjust how that reverb sounds depending on your room configuration. So with all these parameters, it's totally up to your imagination to create your own unique sounding worlds. And for example, you have dozens of surface materials that you can choose from here. Let's say you choose sheetrock or marble to create a more echoic environment for something like the cave that you see here, or for a cathedral. On the other hand, you could use something like a heavy curtain to create a more dampened or dry sounding environment. Now, we recently launched something called Geometry-Based Reverb. And this is a feature to complement the Resonance Audio Room. And it's not only a geometry-based reverb, but it also allows you to bake it in advance. And by baking it in advance, of course, you can achieve even higher performance. And by basing the reverb on the geometry, you can achieve more realistic sounding reverb for your chosen environment. So this works by ray tracing against the static scene geometry. And it enables three things. It enables modeling of arbitrary geometries based on the actual scene, so acoustic characteristics are better captured. Secondly, it enables flexible assignment of surface materials. So it's not limited to just one material per wall, for example, like you saw with our Resonance Audio rooms. And third, there's less manual configuration because you don't have to decompose a complex shape into a series of box-shaped components. So to get started with geometry-based reverb, you need to place what we call reverb probes into your scene. And to do this effectively, we recommend placing them in acoustically distinct places within your environment. So here you have probe 1 and probe 2 at the center of two distinct rooms. However, you want to enable as realistic a reverb as possible. You have to look for where there are transitions between different places. And so probe 3 here is used to basically solve where you expect reverb to vary spatially in your environment. And so the general rule is the more that reverb is expected to vary in your scene, the more probes that you need to place, like probe 3 here. So we also provide material mapping within this feature. And it enables you to map the visual materials of your scene to acoustic materials, much like the Resonance Audio Room. So for example, if you have a cathedral floor, you can map that to a marble acoustic property. And this is a big time saver, so you don't need to manually map multiple visual materials to the same acoustic material. Then the last step in the process is to click the bake button that comes with our plugin within Unity, and it pre-computes all the reverb probes. After those are computed, we also provide these post-baking properties, so you can set things like gain and brightness. And to test things out, you simply click play in the editor, and then you can walk around and listen to the results. So I'm going to try to give you a demo of that right now and pop out of PowerPoint for a second. We have a scene set up with 3 acoustically distinct environments and a clapping sound. And you should be able to hear how the clapping sound varies as you go into the cathedral, the cave, and the other room. So I click play in the editor. Let's see if we can get the audio to work. I can hear it faintly. Cool. So we're going to walk into, well, I'll zoom back first. We have a cathedral here. We have a cave on the left and a building on the right. Okay, now we'll go into the cave. A little hard to hear the echo. And we'll go into this small restroom. All right. So that was a demo of the reverb baking in action. And now we'll pop back into the presentation. And by the way, that demo scene comes as a demo when you download our plugin, so it's super easy to try it out for yourself. And it's natively integrated into Unity 2018.1, so you can download the beta there and try it out. All right, the last feature I wanted to talk about is what we call ambisonic recording. Ambisonics, as you may know, is a popular technique for achieving higher performance, especially when you have a large number of audio sources in your scene. And with our Unity plugin, you can simply click on the record button inside our Resonance Audio Listener component and walk around your scene, and our plugin will automatically spatialize all of the audio sources and put them into a file in an ambisonic format that you can save to disk and reincorporate into your scene using a Resonance Audio sound field object and assign that to any object or area of your scene. You can also export that file to any other projects you have. It's compatible with YouTube and Facebook, for example. So if you're uploading a 360 video and you want to have an ambisonic file in the background, then you can actually use Unity to generate that content as well. That wraps up the high-level overview. I'm going to hand things over to Marcin now to talk about Ambisonics.
Okay, thank you, Eric. My name is Marcin Gorzel. I'm a software engineer on the Resonance Audio team. And I would like to go slightly deeper into one of our core DSP algorithms, which is Resonance Audio Spatial Iser, and talk a bit more why basing it on Ambisonics technology allowed us to not only create a very efficient system, but also a great sounding framework for rendering of binaural sound sources. So traditionally, to create a binaural source, we basically take an audio signal associated with a source, and we process it with a set of head-related transfer functions, and these, or HRTFs in short. And these transfer functions basically fully describe the acoustic path between the source and our head. Obviously, when we have multiple sources, it means that we need multiple HRTFs. And also, if the relative location of the source and the listener changes, switching between these HRTFs can be very, very noticeable. There are actually libraries that offer HRTF switching as a simple panning method, and you can experience that yourself. It's very audible. So a better solution is to use some sort of interpolation, like by linear interpolation, use multiple HRTFs at the same time to render sound source in space. But we still need a very high number of these HRTFs. We still need a very dense grid. And also, research shows that switching is still noticeable in the interpolation. So, for example, you can very well localize sound sources, and they sound very natural as long as they overlap with the HRTF location. But once they are in the middle of multiple HRTFs, localization is slightly worse, and they also sound slightly different. So we've decided to base Resonance Audio technology on Ambisonics. And Ambisonics essentially allows you to use the so-called spherical harmonic functions to recreate a sound field. So I think the biggest advantage that we are getting from here is that we use this intermediate interpretation for all our sound sources. So we no longer have to render each individual source binaurally, but first we bring them all into an intermediate ambisonic representation, and that allows us to render them all at the same time. So let's look slightly more deeply at the Resonance Audio Spatial Iser. And this is used not only for positional audio in Resonance Audio, but also for rendering directional components of room acoustics, like early reflections, or, as Eric mentioned earlier, playing back ambisonic recordings. On a high level, it consists of an ambisonic encoder, mixer, and decoder. To encode a sound source into our Ambisonics, what we basically do, we take the mono signal, we compute a set of so-called spherical harmonic coefficients for the given source location, and we have to multiply this mono signal with all these coefficients. And the more spherical harmonics we use, the better spatial resolution we get. which means that if we want to represent our sound source very accurately in the sound field, we have to use a lot of spherical harmonics. So for example, first order Ambisonics is 4 channels of audio. Second is 9, but third is already 16. So as you can imagine, that's actually quite a lot to compute at real time, especially if source changes its location. We have to recompute them all quite often. We could tabularize them in some way, but given very fine resolution of human hearing, which is in the best case scenario like 1 degree resolution, this is not a very practical solution either. So we were asking ourselves, can we do something smarter here? And what we did, we started to look at symmetries of spherical harmonics. And it happens that there are some certain regularities in terms of spherical harmonic symmetries that can be generalized. So for example, if you look at the middle column, the spherical harmonics m equals 0, we can immediately see that they are all front-back, left-right symmetric, but only when the order of spherical harmonic is odd, they become bottom-up anti-symmetric. So essentially, in practice, what we do, we use all this information and we pre-compute only a very small subset of spherical harmonics, like 1 quadrant of a sphere, and we can do it at a very, very fine spatial resolution. And at runtime, we can very rapidly retrieve all the other spherical harmonics using at most 4 multiplications. So that allowed us to create a very, very fast and efficient higher order ambisonic encoder that runs and can encode even hundreds of sources, even on mobile platforms. But that's not only that, like this encoder is capable of rendering sources at a given distance, and we added other cool features like spread control or even near-field rendering. So how about decoding? So as I said, Ambisonics give us this edge that we basically have all our sources and we render them using HRTFs only once. So in practice, it looks like this. We take all our sources from the Ambisonic mixer, we process them with some filter, which basically means we are optimizing the Ambisonic decoder. Then we process it with the Ambisonic decoder matrix, perform HRTF convolution on the virtual speaker signals coming out of the decoder, and by summing left and right channels, we get our binaural stereo output. So in Resonance Audio, we are actually do all this heavy lifting offline. So first of all, we assume symmetry of a human head. So basically that can allow us to halve the number of HRTFs that we use in processing. But we first pre-process them with the Ambisonic decoder, we filter them later, and we end up with something we call spherical harmonic symmetric HRTFs. And that basically allows us to, without leaving Ambisonic domain, perform all the HRTF convolution, which is much cheaper and leads to exactly the same results. So, yeah, some tests that we run on different platforms indicate that using this optimized decoding approach, we can get a speed up of up to 12 times. Okay, so I want to finish off to show you some other performance results that we got. So this is Resonance Audio Spatial Iser compared to some other 3 popular solutions. The orange or yellow boxes indicate when the CPU consumption reaches around 70–75%. This is when we start to hear occasional dropouts, and the red zone basically means constant dropouts. So this chart represents the number of sound sources that we render in a Unity app simultaneously, and basically we measure the average CPU consumption for them. So as you can see, for a small number of sources, we are basically as efficient as all the other solutions, but we scale much, much better with the number of sources, just because we don't have to deal with this per source convolution. So that was a deeper dive into Ambisonic Spatial Iser Resonance Audio uses. Now I would like to pass it over to my friend and colleague Ian, who will be talking to you about another cool feature we have, which is constant cost reverb. Thank you.
Hello everyone, how are you? First off, let me say, please don't judge our reverb purely on what you heard before. I guarantee you it sounds a lot better with your own speakers and your own headphones, so bear that in mind. So what I want to talk about is how we made our room effects constant cost. And that's constant cost with number of sources in the room, constant cost with the room you are simulating. So you could have a church, a cathedral, or a closet, all constant cost. And that was kind of our aim and what we managed to achieve. So first of all, let's think about what we're actually representing. So room effects. They can be split mainly into two parts. The first is what we call early reflections. Early reflections are the first set of echoes that bounce off the walls and reach your ears after direct sound you hear. Now, these are extremely important for getting a sense of your position in a room, for a sense of the size of a room. As you walk around a room, if you're closer to a surface, you'll get reflections off it sooner and louder. If you're far away from any surfaces, the early reflections tend to all arrive at the same time, thereabouts, and also have much lower intensity. Early reflections are a very important part of room acoustics, but sometimes it is overstated how accurately we actually need to represent them in order to make a believable set of room effects. Human brains are trickable. That's one of the things every engineer has to live with, well, is glad to live with. The second part of room effects is the reverb. This is after a few hundred milliseconds, when the number of reflections bouncing off the walls has reached into uncountable numbers, when the density of the reflections at any one point in the room could be equal. At this point, it literally becomes a statistical process. It's chaos theory in action. It literally is unpredictable. And if you took any 2 points in a room, like say, for example, the 2 points that are beside my 2 ears, the reverb at those 2 points is statistically independent. It's as decorrelated as white noise. And this is a very important thing to remember. If you're going to give someone a believable sounding reverb, you're going to want to match these statistical properties. And that's another thing to bear in mind as we move on. So first off, I'll talk about our reflections. And first of all, what I'm going to go through is kind of like what we actually need in our reflections in order to actually be believable, and what we don't need as well. We need coarse spatialization, by which I mean you need a sense of the reflections coming from in front of you, behind you, to your right, to your left, above, below. You don't need to have degree-accurate locations for a reflection, because in a real room, you're receiving reflections that are changing all the time as you move. They're changing with surfaces in a room. Your brain doesn't pick up on these things. Your brain doesn't find these things important, and therefore it is not important to simulate. We need to have changing intensities with proximity to surfaces as you move close to a surface, as you move far away from a surface. That's an important thing to keep. We need real-time changes in reverb. If you have a static, in reflections. If you have a static set of reflections that aren't changing their position in time, aren't changing their intensities as you move around a room, your brain is not going to be fooled into thinking it's a real room. And finally, we need to coarsely get the delay times on the reflections, i.e. how long it takes to emit from a source, bounce off a wall, and get to my head. We need to coarsely get those times right, but they don't need to be very accurate. Your brain doesn't know the difference between a wall that's 2 meters away and a wall that's 2.2 meters away. So that let us do a few little optimizations in order to get constant cost to rendering reflections. We tracked something very simple. Excuse the crudity of the head in this diagram. The blue square is the front of the person's face, and the circle is the head. That's the best I could draw. We track the distance of this listener from surfaces in the room. We track the position, the direction the listener is actually looking in. And based on that simple information and the knowledge of our room geometry, we do a very, very, very simple reflections encoding that sounds indescribable, indistinguishable from a more advanced technique. We take the input from the various sources in the room, we low-pass filter them based upon what the average absorption coefficients of the room walls are. We then apply delays for each of the cardinal directions around. We then apply magnitude based upon the surface properties of the surfaces in those cardinal directions, and this gives us 6 values. All we've done so far is delays, a bunch of multiplications. It's extremely cheap. And then we combine these together into the 4 output channels, which match the 4 channels of first-order Ambisonics. And by combining them in this way, where lines coming together are simply a summation at the bottom, and dotted lines represent where we subtract as opposed to add, we can get reflections on each of the cardinal directions at just 12 pointwise summations. Extremely cheap, and yet sounding good. Our reverb is a new feature. Reverb itself in our project is not a new feature, but we have introduced what we call the spectral reverb. And the entire idea behind this was to get even better decorrelation, as I mentioned before, between ears, and to get constant cost. We offer what we call maximally decorrelated stereo reverb. That is, it's as decorrelated as if you got a pair of noise channels, pure white noise. It's constant cost regardless, I'll say again, of the reverberation time or of the number of sources you're rendering. The reverberation time is controllable in individual frequency bands. In fact, the pure C++ code is controllable at any level of resolution. And it runs on a mobile CPU with lots of room to spare. So to go into those a bit more, the maximally decorrelated reverb is essentially the same as having a different reverb tail passed to both ears. And you will notice, someday play with it. Generate 2 reverbs, play 1 to each ear, generate a single reverb, and play it to both ears. You'll get the very strong sense of a sound being inside your head and outside of your head. This is a very important part of actually making someone believe that they're listening to something that's not just over their headphones. And as I said before, the reason this is important is because your 2 ears, right now as you sit in this room, are sampling completely different signals with regards to the late reflections that are bouncing around. They are independent processes. The reverb also offers, as we said, constant cost. This thing will cost you the same if you have a 25-second reverb of an alien environment, if you have a 5-second reverb of a cathedral, or if you have a 12-second reverb of a cave, or if you want a 0.1-second reverb in your closet. It costs precisely the same. The algorithm is set up in such this way. It's also controllable, as I said, at every individual frequency. Now, in the Unity plugin, it's controllable across what are called octave bands. These match closely human hearing because, well, it's being presented to humans. But in the C++ code itself, it's controllable at any level. And I'll tell you why I mentioned that in a second. And finally, on a Google Pixel first generation, which is already becoming an older phone, at 48 kilohertz, our reverb and reflections together are using less than 1% of the mobile CPU. Again, that's irregardless of the number of sources, irregardless of the length of the reverb. And as you can imagine, on more modern phones and on desktop devices, that's an even smaller fraction, and it's guaranteed constant. So, as Eric said before, there are 2 ways you can control this. You can use the more simplistic resonance audio rooms to quickly create a little environment. For a lot of simple games, that's probably enough. Or you can start playing around and have fun with placing reverb probes, baking your reverb, matching your acoustic materials to the surface materials in your actual scene, and getting smooth transitions as you walk around, all done, pre-computed, and all running at constant cost. And now, the reason I kept talking back about C++ code is because we just made every single line of this open source. The Unity integration is open source. All of the underlying C++ code is open source. And please, feel free to dig in. Feel free to notice things you'd like to change and make pull requests. Feel free to ask questions. Feel free to find out more about how all of it actually works, because it's yours now. It's yours to play with, to change, to reuse. And for those who've never used Resonance Audio before, you can find lots of documentation about our SDK and use it in Unity. And for those who have, go on to GitHub and start playing with it. Thanks very much. And I'll leave you now with Eric, who I think wants to make a small little announcement about another... Oh, well, I'll let you talk first. Thank you. Thank you.
So I think we have a little time for Q&A.
That picture. Hi. So you had describing the way that sound is emitted from a source, that guitar in the room, when you had sort of this like polar representation that you could play around with. And so that seems to simplify the situation by assuming that you're mostly at like a level plane with the sound source. Do you think in applications such as in VR, where the user can have a huge variance in like their proximity to the ground or the ceiling, that you might want to have control over how that varies in height as well?
Yeah, absolutely. So we definitely address the height issue in VR. Ian, you want to take this one? I think Ian can tell you how we address this.
Well, first off, that's just a visual representation to try and help you understand what's happening. The actual source emits in 3D, and the directivity patterns are three-dimensional. It's simply, to actually draw that in your Unity scene as you're trying to design this thing, it looks ugly as hell, and you can't see anything else in your scene, and it's impossible to use, and it was a UI disaster. Putting a nice 2D plane in was actually usable. So rest assured, this is already covering elevation. This is already a 3D emitter. That's just a UI choice.
Cool.
No worries.
You can hold on.
Hi, thank you for the presentation. Very interesting stuff. So it sounds like all of this is really optimized for people using headphones, or how do you handle people with, for instance, a surround system? Where does is there a fold down happening, or how do you handle multiple types of output?
So currently, this is a headphones-only library. We provide a fold-down. If you unplug headphones, that will be a stereo down mix. But currently, Resonance Audio doesn't offer any surround sound output. Also, open sourcing gives some opportunities there. I think we can, if there's enough interest and demand from community, we may consider adding surround sound output.
Well, so I guess just to sort of a little more on that question, I've noticed that, for instance, ambisonic recordings sound a certain way when you're wearing headphones, and then when you hear them in stereo, like coming through stereo speakers, they sound different. They can sound kind of bizarre. And so, is it actually the same mix?
No, it's not.
It's two different mixes.
Yes. So if the headphones are unplugged, the stereo mix that we are doing is like that. It bypasses HRTFs processing, so there are no HRTFs applied. We basically do a MS decoding of ambisonic sound field.
Great. Thank you.
Hey, Marcin. You were talking about kind of intermediate encoding into an ambisonic sound field of your sound sources. How does that play with the Unity kind of mixer hierarchy? So if you want to kind of make sounds into buses, intermediate buses, and then kind of apply effects and stuff like that.
Okay, I think we have an expert that could answer this question that's sitting just behind you.
Yeah, so for Unity right now, the submixing hierarchy that we don't use because we mix. So what you can do right now is using source-based effects. But for the mixer effects, we currently bypass all. But even though it's slightly unrelated at this point, but we do offer those type of solutions in non-Unity versions if you're also interested digging deeper. And yeah, I think that's pretty much it.
Thanks, Alper, our plant in the crowd. Just on top of that as well, the reason that that's done is actually an optimization. By mixing ourselves and doing everything in the ambisonic domain, we can save a huge amount of processing. And that was kind of the design choice we made, that we went for efficiency over all else. Because, well, you don't want to only have 12 or 13 sources in your scene. You want to be able to have hundreds. So it was a tough choice, but I think in the end, we decided performance was our driver.
Any more questions?
One more question. If we go here, we'll see demos of this. Are there any public products or projects that we can look at that are good examples?
One publicly available demo that we have is called Audio Factory.
Okay.
You can download it either for Daydream or it's available on HTC Vive as well.
Okay.
As of this year. And basically demonstrate. It's like it's not a game. It's like a experience where you basically explore and experience different features of resonance audio, including reverberation, positional audio, and so on.
Thank you.
A couple other recently launched third-party applications that use resonance audio. Pixar launched Cocoa VR as a demonstration for their movie using resonance audio on the Gear VR setup specifically. Again, because on mobile you need something that's highly optimized. Lucasfilm has an AR app for iOS and Android called Jedi Challenges that's using resonance audio. And I believe Flutter VR, which is an app for Daydream that came out a few months ago, is going to be doing demos at GDC in partnership with Unity. So you might actually be able to check that out here.
Great.
Yeah.
Thank you very much.
Yes, in the back.
So I have two questions. First is it third order ambisonics is what your what your output is at the end?
Yeah. So within.
Is it third order? Is that?
Yes, so we provide actually 3 quality modes in Resonance Audio SDKs. The lowest one is first order, and the highest one is third order.
And then also, so what are you guys, the process that you're doing, are you actually synthesizing the sound field, and then just your final output is just whatever you're decoding? Is that kind of generally what you're doing, is manipulating the sound field?
Yes, so basically we get all the sources, encode them into Ambisonics. We encode all the reflections into lower order Ambisonics, get any recordings that you also provide from the sound field mic, for example, and having this whole sound field representation, then we process all at once with HRTFs to get binaural.
And it's probably worth mentioning as well that the HRTFs are actually in the spherical harmonic domain themselves, and that processing is done that way, and that again saves us on CPU usage. So it's always the theme there, you know.
And it's so the possibility of customizing like a decoder if we wanted to have like a second or third order ambisonic speaker array, we'd be able to have access to actually create our own decoder.
Yes, so in the open source release, we have a class called Ambisonic Codec, and that basically provides basic encoding, decoding functionality, and you can customize decoding matrices there. Oh, yeah, so we also have scripts that allows you to create spherical harmonic HRTFs of currently up to 5th order, if you're interested in exploring. But it's not really restricted by order. Only the amount of HRTFs you have in the database will determine what your order is.
And what libraries are you using for your HRTFs?
We are currently using SADI HRTF database from the University of York.
Okay, thank you.
Any other questions? Yes, please.
You were showing that example where you had kind of the guitar and sort of the wall in front of it. What's the granularity kind of on the occlusion? Is it, does it do partial occlusion or obstruction, I guess? You know, when you bend around the wall, you know, what's the kind of resolution of that? Is it just like it's obstructed, it's not obstructed, or is there like a more kind of...
Yes, let's give everybody a chance to answer a question or two.
So in terms of the detection in Unity, we have I would say, a simple detection model. It's like ray-based, like just point ray cast. But the idea is we actually just, in the last release, I think, expose that value itself. So the effect itself is fractional. So you can do, you know, it's in the C# scripts right now. You can basically modify the detection model to a more complex version. So the idea for us was there wasn't a strong desire from the users to have a, you know, more computationally heavy algorithm there. So if you want to, you are free to use any fractional models or sophisticated detection stuff. Yeah.
Would anyone else from the audience like to answer a question?
Sorry, I have a 2 o'clock thing. I wanted to ask what the final announcements were.
Simply, I think Eric was going to give a shout out to some other Daydream products that are on display here. That was all.
Yeah, so if you're interested in checking out other Daydream products, there's a demo room just across the table outside the glass, and our team would love to give you an experience. Great. Thank you all.